In this video, we will be reviewing content from week 4 of Physics 259, which details Gauss's law a little bit more relating to superposition, as well as talking about electric potential energy and electric potential. So for this first question here, I'd like to introduce this new value, which we call volume charge density, which is represented by rho. So this is the amount of charge per meters cubed now, because we are dealing with volume. So this question here wants us to find the electric field inside the cylinder and outside the cylinder. So if we started with part A first, that means we are starting with a cylinder that is smaller than our given one. So if we imagine our Gauss cylinder shelled inside of it with a radius r. First thing that we do, we are going to find our right side of the equation, which is Q enclosed over epsilon naught. And we don't know what our Q enclosed is, but we're going to use this equation here to get our Q enclosed equal to our rho times our volume. And we want the volume of our whole cylinder, of our Gaussian cylinder, so this is going to give Q equals rho, and this is pi r squared times L. So then our right side is equal to Q enclosed over epsilon 0, which is equal to rho pi r squared L over epsilon 0. So that is our first part. Second part, we want to find our left side. So from previous examples, we know that our electric field is directed radially outwards from our Gaussian surface, and we want them pointing parallel to our dA lines. So on the top and bottom, they point perpendicularly, so we are not going to use our top and bottom. So we only use our side face. So then this is our first side, and that is E dot dA. Since electric field is constant along that surface, then that means this is just going to equal E times our integral of dA, which is just equal to E times A, and that is equal to E times our surface area of our curved surface, which is 2 pi r L. So now we want to equate the two sides. So then that will give us E times 2 pi r L is equal to rho over epsilon naught. So let's simplify and isolate for E. So both our pi's cancel, both our lengths cancel, one of our r's cancel, and then that leaves us with E is equal to rho r over 2 epsilon naught. Okay, so that is our first part of this question. And for our second part, we want to find what it is outside. So if we change our cylinder to fully enclose, so that is our starting cylinder, and then our Gaussian cylinder wraps around it like this, and this now becomes R. We want to do the same thing. So our left side. So we usually start with right side first. Let's do that. So we start with the right side of our equation. So that's Q enclosed over epsilon 0, where Q enclosed is rho. And we want to find our charge enclosed. So since our Gaussian surface carries no charge except whatever lies in our original cylinder, that means we are going to be using pi large R squared length for our volume over epsilon naught. Because the R is for our smaller one, so the capital R. That's why we have capital R squared. If we do for our left side now, it's the same thing, but now we have, we want to use our Gaussian surface. So this then becomes, so it's our side times dA. I'm just going to shortcut. And then this gives our area, and we want to use the area of our Gaussian surface. So then this is 2 pi little r L. So when we equate both sides, we're going to have 2 pi r L equals rho pi capital R squared L over epsilon naught. Then when we isolate for E, so we see that our pi and length terms cancel. So that's 1 over 2 epsilon naught times rho capital R. Sorry, capital R squared, and that's divided by R, little r. So then this is our second equation for part B. All right, our next example is a little more complicated. So we have a hollow cylinder. So it's missing another cylinder that is inside of it, so it's not solid. And we want to find the electric field at point A, so that's already drawn out for us. Part B, which lies inside. And at point C, which is inside the hollow sector. So the first thing that we are going to do is we're going to solve for our outer Gaussian surface. So that gives us, so we want to take our fully charged section and subtract the hole that is missing from it. So if we had this region right here, so this is the solid part, right? This is the part containing our charge. And we want to subtract from it, or rather add the negative volume from our missing sector. So if we were to write this out for part A, this would be our positive electric field plus our negative. So then this becomes so our equation that we found for the outside was 1 over 2 epsilon naught, and then we have rho b squared at our distance to our point of measurement plus, and then we have our negative 2 epsilon 0 rho, and now we're looking at our smaller one, which is a squared over our distance. And if we simplify this out, this is 1 over 2 epsilon 0 rho over r, and that's b squared minus a squared. So that is our first equation when measuring outside both of our points. if we take a look at part B, so B lies within our section. So in this case, we're going to do the same thing where we have our positive plus our negative, but B is now replaced by R, right? So rather than taking this whole B into account, we're just measuring at this distance R. So if we do this again, this is 1 over 2 epsilon 0 rho R squared over R, and we can just simplify that to our R, right, because they cancel out. And this is plus negative 2, 1 over 2 epsilon 0 A squared times rho over R. Same thing if we factor it out. Then that becomes R minus A squared over R. So that is our second equation. And finally, inside both of our surfaces, we have point C. Our electric field at C is just going to equal 0 because we are not enclosing any charge, and therefore we cannot have any electric field at that point according to our Gauss's law. Okay, so that is our second example done. Next, we're going to talk about electric potential energy. So before we further discuss electric potential energy, I would like to illustrate how we can think of electric potential energy with an example. So potential energy is the tendency for something to gain energy. So you can think of a ball resting on a high counter as having higher potential energy compared to a ball that is sitting on the ground, right? So it has potential to be falling if you were to push it off that counter compared to the ball that's already on the ground, which would have 0. So if we take a look at an example here, say we have a particle that moves with an electric field, a particle that moves against an electric field, and two particles that move perpendicular to an electric field. Call this A, B, and C. In our first example, A does positive work. In B, we are doing negative work because we are working against our electric field, so we have to overcome that force. And C, we are doing 0 work because it's constant. Because we're going perpendicular, so we're not experiencing any difference or change in our electric field that's acting upon our particle. So, if we looked at why this is, so the formula that we mainly use to define electric potential energy, so we represent it with a U, is equal to negative work. So if we were to analyze this from a potential energy standpoint now, this would be negative U, positive U, and this remains 0 U as well. So we use more energy going against our field in our example B. So that's why it's positive compared to our negative electric potential energy going in the same direction because we are losing energy. So our change is different, right? So we can define our change in U as our final minus our initial. So because we end up at a higher point than we were before, so think of this as our countertop, because we are taking our initial and moving it up to a higher spot that has more potential. That means we're going to have an overall larger electric potential energy compared to taking a object that starts high and moving it lower. So think about having a counter and a stool. If you took a ball from the stool and moved it to the counter, it now has higher potential energy because it has a greater tendency to fall a larger distance if that ball were to fall off the counter. And if you did the opposite, so this represents case A in our example, if we had the ball on top of the counter and we moved it to the stool, that would lower the potential energy because it has, if it were to fall, it would have less energy doing so. So with that in mind, we can talk a little bit more about electric potential energy. So the equation that we are going to use to represent our work, so we're going to find our electric potential energy using work. So we're going to start with work first. So in this course, we use work as our ending path and our starting path as our bounds, times our force and our path that we travel, represented by ds. So this is the equation that we will be using. And the reason we integrate is because this helps us when we're traveling along diverse paths. So that allows us to add up each individual component. So if we use that expression for this example here, so our expression for work was equal to our final and initial positions. This is force dot product of ds, which is equal to of f ds times cos theta. Since the angle that it makes with our electric field is 0 degrees, because it's parallel, then that just makes this expression f times ds. So that gets rid of our dot product, so we just have the magnitude of them multiplied together. And I'm going to continue this on over here. So this is f ds. And we can replace our f with q times E. Our electric field is equal to F. So when we do that, that gives QE times ds. And since our values of Q and E are constant because our electric field is constant with our motion of our charge, then those get kicked out of our integral. And then this just becomes, so within our integral bounds, becomes RF minus R initial. Or we could call this work equals QE times our change in our distance. So if we were to do this for a proton, we want to find the electric potential energy. So let's find our W first. So our Q is positive. So that's our charge is elementary charge of lowercase e times our electric field, change in D. So then we know our electric potential energy is equal to negative work. So then this would be negative E, electric field, change in D. For an electron, it's the same process, except we have a negative elementary charge times electric field and change in distance. So then that makes our electric potential energy equal to positive E, electric field, and change in D. we were to do an example from a electrostatics standpoint, we could find our force using Coulomb's law. So then this is 1 over 4 pi epsilon naught. And we have two different charges. We have the movement of our charge lowercase q and our large Q over a separation squared. So we can put this in for our equation for work now. So then this will look like work equals, so our ending point is B, starting point is A, and when we plug in our F, this gives us 1 over 4 pi epsilon naught over r squared. And instead of ds, we are going to be using dr because it's our change in our radius, because you can imagine them at different distances from that q, where this is rb and this is ra. So with that same knowledge, we can find what our constants are and move them outside of our integral. So then this is 1 over 4 pi epsilon naught. And then this will leave us with negative rb plus 1 over ra. And this is our work. And then to go to our electric potential energy, then we just add a minus sign. So that's for, so we're changing our signs. So then that means inside of our brackets, our bounds are 1 over rb minus 1 over ra.